Right, welcome to our final week on biological earth and space sciences. Being as it's the final week, what I've tried to do is try to come up with a little bit of a synopsis for you, a little bit of a wind-up to the course and where we're heading. Most of you are absolutely flat out at this stage working on your assessment tasks too, and I cannot blame you. It carries 50% weighting, and we're getting some very, very good questions on the forum, so on the Q&A forum. So if you have anything, get on there and have a look. Someone's probably asked it already. If not, make sure you ask it, please. Just with June 1st is the due date, and we'll be looking forward to getting the unit wrapped up and a well-earned break in place. Let's get started. So I'm going to ask this week, first of all, we're reading Locksley chapter 11. It's our textbook, and it's a reasonably good textbook, but it'll also be a little bit simplistic. And when I read it, it actually has a heavy assumption that we actually know what Earth science is. So this week, and particularly with Assessment Task 2 in mind, because some of you will be developing a digital card on Earth science, so I'm actually going to unpack a little bit about what Earth science is. So it's a strand of the Australian curriculum, and if you read through Locksley chapter 11, it gives you a really good idea of what is involved with Earth science. We'll give you a little bit, we'll expand on that in a minute. At the end of this topic, you should be able to do 4 things. Identify different types of energy, describe various sources of energy, compare and contrast renewable and non-renewable sources of energy, and also explain global warming. So obviously we're taking a very environmental focus, even though we could take a very systemic focus to Earth sciences because it's a very broad area, and I'll explain what I mean. An overview of Earth science, it's got basically 4 streams of science within it. So it's a compactum. It is 4 different areas of science brought together. We've got geology, which is study of the formation of the Earth. We've got oceanography, the study of the oceans. Meteorology, the study of the atmosphere and processes that produce weather. And astronomy, which is a study of the universe, which is well documented, going right back prior to the Greeks and the Romans. So we have, and we look at our own indigenous society, who are fabulous astronomers, navigators. Their whole dream time stories are embedded in connections between Earth, sky, and planets. So it is a rich field, astronomy. So we've got 4 huge areas of science that we bring together here called Earth science. So as a teacher, you are really going to need to know your way around this terrain in order to be able to teach it effectively. So when we look at the formation of the Earth, let's get our facts right. What have we got here? Most research concludes that the Earth and other planets formed at essentially the same time. We talked about the Big Bang last week. We talked about the first milliseconds or microseconds where the gases formed, and the nebula hypothesis was assumed to have taken place. An enormous rotating cloud called the Solar Nebula, which was the eruption from the very first atomic formation. Now, the nebula was composed mostly of hydrogen and helium, the gases. It happened about 5 billion years ago. The nebula began to contract. It is assumed that they contracted into a disc-type shape, but what we call our protosun, our pre-sun, at the centre. And point number D, and here we've got our diagrams going A, B, C, D, and E, ultimately to the solar system. The inner planets began to form around a metallic and rocky clumps around this disc-like sun that formed at stage C. And finally, ultimately, the larger outer planets began forming fragments with a high percentage of ices as the gases cooled and cooled and cooled some more. So what we can see here is what is largely the scientific consensus around the formation of the Earth and the origins of Earth science, which is what we're studying here. The formation of the Earth, it formed from layers. And layers gradually formed like crusts over the top of the Earth, and as the Earth formed, the decay of radioactive elements and heat from high-velocity impacts caused temperatures to increase. Fortunately, heat escaped from between the cracks within this formation, and we had further gathering of gases, further heating of the environment, and ultimately the spawning of life. But what we've got here are lighty, rocky components floated outward towards the surface. Gaseous material escaped from the Earth's interior to produce a primitive atmosphere. But look, a lot of this is very, very old science, very old factual teaching. Earth the movie tends to cover it in quite an awesome way. Right, so we've begun that vital construction process. We're starting to build students' conceptions of what Earth science really is. We're getting them hooked, we're getting them excited. Now we're going to deconstruct it and give them what Bloom would call some very, very basic knowledge and comprehension steps. So we're going to look at some of the scientific constructs. The Earth's major sphere, there are four of them. We've got the hydrosphere, the ocean, predominant feature. It's about 71% of our surface, and it holds about 7% of the Earth's water. So it gives you an idea of again, some little inquiry tasks here, salination versus desalination. It also includes fresh water found in streams, lakes and glaciers, as well as that found underground. The Earth's major spheres, the second one is the atmosphere, the thin, tenuous blanket of air that surrounds us. One half lies below about 5.6 kilometres above us, and the other half is above that. Now, when we look at the different levels of atmosphere and the different constructs of atmosphere, different things are possible. Different constructs are at work. We look at the biosphere. It includes all life. It's a term we give to all life. It's concentrated near the surface in a zone that extends from the ocean floor upward for several kilometres into the atmosphere. So we're starting to give the students a little bit of a framework here on how to address the Earth. We're breaking it down from a planet, from a global concept of a planet, to actually four major spheres. And from these spheres, we're actually going to break it down into systems. So what we're doing is we're actually working, as Piaget and as Bloom would indicate, we're working very much in the cognitive domain, building knowledge, comprehension and application. So geosphere is the compositional differences. It consists of crust, mantle and core on the Earth's surface. The crust is the thin rocky outer layer of the Earth. The mantle, about 3,000 kilometre thick layer of Earth below the crust. And the core, of course, is the innermost layer of Earth located beneath the mantle. And here we've got some fabulous stories from science fiction dating right back to the 19th century with people like Jules Verne, who wrote Journeys to the Centre of the Earth. So there's some fabulous imaginative prospects at work here. But what we're going to do is strip the imagination down and instead put in knowledge, comprehension and application. That's our job as teachers. So what is a system? So within each of those spheres there are various systems at work. We saw in the video we've got plate tectonics, we've got planet movement, we've got, for instance, within the biosphere we've got and the geosphere we've got latitude and longitude. We've got these different location determining. Now, of course, got the science of GPS. We're seeing that explode right across the globe and blending and mixing with technology and Google Earth and Google Streets, all of these different things that we can do which lead into maps and mapping, and of course topographic maps, which are 3D maps of the Earth's surface. So we're starting to see that a system, we can look at these spheres in terms of the systems that interact to form each of their wholes. And what we're doing now, we've gone from one thing, the planet, down to four spheres, which are interrelated components. We're now seeing that those spheres are made up of systems. So we can see what Bloom wants us to do here. We're looking at the interacting parts that form the complex whole of the planet. Closed systems are self-contained. Systems that rely entirely on their own operating. An air conditioner, for instance, in a house. An automobile cooling system. A computer system that's not connected to the internet, for instance, is a closed system. Open systems allow both energy and matter to flow in and out of the system. For instance, rivers, are a great example. Oceans are a great example. Cities are a great example. Earth system science. So when we look at Earth system science, what are we really talking about? We're talking about a dynamic body with many separate but highly interesting interacting parts or spheres. Earth science studies Earth as a system, and it's made up of numerous parts or subsystems. Now we know this because in our ACS, for instance, we have strands and substrands. We've got different sources of energy. Energy as a subsystem. That's a big focus this week in Loxley. When we look at the sun, for instance, which drives external processes such as the weather, ocean circulation and erosional processes. They are our sun-related external processes. Our interior earth-driven processes, volcanoes, earthquakes, mountain building. Alright, all of a sudden we're starting to understand our own concepts of earth science. We're starting to understand that it can be broken down into subsystems where we can now actually do our curriculum work as teachers. We're narrowing down this thing we call the planet into several zones. And to borrow a Vygotskian term, these are zones of proximal development where we can really build knowledge, comprehension and application. And finally, humans are part of the Earth system. And here's where we enter that study, and particularly this week's material from Loxley, where we look at environmental studies. We talk about people and the environment. Now, a little diagram up here shows us that we've got different levels here of our environment and the impact that we can have on these different levels. We can actually break down this complex science into some very, very simple mnemonics. A mnemonic is a model or a heuristic that can help us and help students and learners really understand about the world of science, in particular about the world of earth science. So we look at the environment here. We talk about the surrounds. The environment is defined as surrounds and how it defines and influences organisms. Now we know this relates to animals, we know it relates to insects, we know it relates to plants and minerals, and you know, we can see that the physical environment encompasses water, air, soil, rock, the four elements. The elements go back, for instance, to Mytho-Greco times, and then they're in poetry, they're in plays, they're in drama, they're in folklore. The term environmental is usually reserved for those aspects that focus on relationships between people and the natural environment. So, you know, we can talk about environment, we can talk about physical environment, and then we talk about environmental, which is relationship bound. Resources we talk about include water, soil, minerals, and energy. And again, we make this split, and this split is well documented in Loxley this week, between renewable resources, resources that can be replenished, plants, energy from water, energy from wind, okay, where all these hydro and thermo-driven energies. Then there's non-renewable energy, energy that cannot be replaced in the near future, for instance, metals, fuels, anything carbon energy based. So, again, these may appear like simple concepts to you, but when we are attempting to teach earth sciences, we need a point of entry. We need to break down this whole thing we call Earth into its various spheres, its systems and its subsystems, so that we can give the students a language to explore, document and reconstruct their own understandings. That's what we're doing. We're giving them those tools. The growth of the world population, as we can see, we talk about environmental problems also. Now, environmental problems usually take place on a local, regional and global level. Again, these create great local experimental and inquiry paradigms. Locally, what happens, of course, we look at our own weather cycles, we look at floods, we look at cyclones, we can look at humidity, we can look at the wet season, dry season and the importance of rain. All of these different things. We can look at a regional level. We can look at the barrier reef, the Adani mine. We can look at the impact of dredging out there and what that's going to do, first of all, environmentally, and secondly, the balance between the environment and the economy. And the balance between well-being and the economic bottom line. And, of course, global environment too. And we can have a look here at the first and third worlds. And we can see all of the implications happening there. We can see the growth in population globally. We can see the impact of China's second child policy. All of these different things bring us into an environmental focus. In our little diagram on the right side of the screen here, we can see how human use and adaptation can actually lead to impacts on our environment. Okay? And we can see how this can lead to things like degradation, urban pollution, air pollution, acid rain, ozone depletion, global warming. Some of the things we haven't listed here, for instance, include deforestation. It's a big thing here in Queensland at the moment, up in the west, northwest. We've also got urbanisation. We've also got the density of cities. Okay, all of these sorts of issues are causing major environmental problems. And of course, some of them are caused also by natural hazards. We can go back and look at our own experience recently of Cyclone Debbie. We can chart the cyclones and the impact of the tidal rises globally. Okay, we can look, for instance, at the Asia-Pacific nations, or little island nations there, who's are the leaders of forums, global forums on global warming, because these are the islands, 2 meters of ocean rising, and most of these islands will in fact disappear, and with them cultures, peoples and communities. So there are environmental problems, and these represent a rich inquiry sandpit for students to move around and play in. So we've got to ask ourselves, what is scientific inquiry? Now, I am going fast through this. I mean, this is a closing session We've been dealing with this all term, so I make no apologies. You guys are in there. I've been talking to you about your work, and I know very well that you're moving along at a great pace and doing some really good stuff. So this is an encapsulating piece. This is just a summary. So in assessment task 2, what are you going to be talking about? You're going to be talking about scientific inquiry, because inquiry-based approaches underwrite the Australian curriculum in science. So science assumes that the natural world is two things. It's consistent and predictable. And this is what science calls homeostasis. It begins from a point where, the Latin term is paribus cerebus, or parito cerebus, I think, which means all things being even. My apologies for that, just slipped my mind. But what we're talking about is science assuming a world that's consistent, predictable. Parito cerebus, meaning things are as they are. The goals of science are to discover the patterns that exist and to use knowledge to predict what may happen were these patterns to be subject to a change in one variable or another. And as a result, we create hypotheses and theories. A hypothesis is the softer version. It's a tentative or untested explanation. A theory is an hypothesis that has been tested, confirmed and supported. And as Karl Popper said, a theory remains a theory until such a time as it's disproven. So his notion of falsifiability, every theory, ultimately the goal of a theory is to be proven false, is the aim of science, to keep testing, retesting and retesting. So scientific method attempts to gather facts through observation. It attempts to formulate hypotheses, and it attempts to get us to test hypotheses to formulate theories. And we do all of this with, as Piaget said in 1962, with the child at the foreground, that the child is a scientist in his or her own life. When we look at scientific inquiry, it's gained through the following systemic steps. We collect facts, we develop a hypothesis, we conduct experiments, we re-examine the hypothesis and accept, modify or reject it. Scientific knowledge is gained by compiling theories that withstand examination time and time and time and time again. And scientific knowledge is gained through totally unexpected occurrences. Random chance. What we call chaos theory, what we call quantum physics, quantum mechanics. All of these different theories on science are now showing, for instance, that science is less predictable and more unpredictable than we imagined. So the question for us right throughout these last 11 weeks is, which science do we teach? Do we teach scientific facts? Do we talk about UVAs and UVBs, the impact on the ozone layer? Do we identify and break down and build little models of ozone depleting chemicals? Do we talk about a stratosphere, a troposphere? Do we look at ozone molecules and break them down into their subparticles? Do we examine the relationship between what is an ultraviolet ray? How does it break down? And how does it make a hole in our environment? So we can do this in a whole range of ways. We can do this as a series of scientific facts, or we can do it as an inquiry process. Right throughout this course, we have tried to encourage you to think about science as an inquiry process. We can look, for instance, at a range of techniques that scientists may use, how scientists may classify our natural world. For instance, rocks. Scientists have come up with classification systems for rocks. Why? A very fundamental question. Here is another classification system. You may have guessed by looking at it when you see Polaris, you see the white dwarfs, you see the red giants, you see the supergiants, and somewhere in there you may also see Sirius, for instance, and the Sun. So we know it's planets. We know it's got Alpha Centauri in there, the brightest star. Here's a classification system for planets. Why is it what it is? What is the classification? Why have scientists done this? Over on the side here we've got a three-dimensional object. We can look at that in terms of volume. Volume is a classification device. Length by width by height. It's a classification device. Everything that has dimensions can be measured. And for instance, we can look, for instance, at the notion of a scale. A scale is a great tool for measuring mass. We know, for instance, what the mass of an object is. But how do we measure, for instance, down here, what this question says down the bottom here, what instrument would be used to measure the volume of an object such as a rock? It's an irregular shaped rock. How would you do it? Think about that for a moment. Let that sit with you. How would you measure an irregular shaped rock? Scientifically, of course. What you do is you take water in a beaker, in a measuring beaker. You would fill it with a certain level, with a certain amount of water. You would tip that water out, drop the rock in, and you would look at the distance when the water level returns to its demarcation, its original start point, and you would be able to take the rock out again, see where it drops to, and the distance between where it started, where it drops to, obviously, is the volume of the rock. So we can measure everything. We don't need to be a rocket scientist. The only thing about rocket science that's rocket science is rocket science. Questions: if an object is heated, what happens to its mass? Why? Well, it's a trick question. When an object is heated, its mass doesn't actually change. Why? Again, great question. Great science. How do we measure volume? Okay, we can do it over here, length by width by height. But essentially we measure it with a ruler. If we don't have a ruler, we create a ruler. And that ruler may be a beaker with marks. Those marks may enable us to actually calculate the volume, okay, simply by the process of withdrawing that rock from a container. So we can come up with our own classification systems. We can adopt the classification systems of others. Either way, our students can become scientists in their own classrooms. Scientists also express relationships. Now what we've got here is a direct relationship. An indirect relationship, a predictable relationship, and the final one, no name. So what is a direct relationship? Can you think of an example? What about pollution versus population? What is an indirect relationship? What is a predictable relationship? We can see the curves and the cycles. Something obviously over time is going to repeat a pattern, and we can actually predict that. And this relationship here is a flat line. So what does that mean? No relationship at all? An indirect relationship. The more of one variable, the less of another. Interesting one, isn't it? Can we just use relationships to drive our inquiry of science, our inquiry teaching? Some examples here: relative humidity and air temperature. We can see midnight, noon and midnight. We can see the cyclical nature of that curve. So that gives us some idea, some notion that we can actually use this diagram to predict and assess. We can look at varies, we can manipulate varies, we can use it to predict, and we can hypothesize. So these are some of the tasks that we're looking to do in our final unit. Down here, for instance, we've got the average rate of erosion over a period of time. Okay, and this is the amount of land relief. So we can see here that everything in our scientific time and frame can be reduced to a couple of simple principles of inquiry. Those simple principles can open and expand almost at the same rate as the universe itself and lead into exponential learning opportunities. Our final lecture this week really is to show that your ability as a teacher to lead students through this process is to have a good understanding of the language of this process itself. What is Earth science? What are the 4 dominant spheres? What are the major operating systems within those spheres? And what are the subsystems that lead to outcomes, that lead to processes, that lead to the conditions we experience in each of those systems? If we can understand that, we are then in the position where we can start to make predictions and hypothesize. If we can start to identify some of the relationships and also undertake some of the measurements required, to capture that vital information. Once we have that information, we are then in a position where we can begin to make some predictions, some hypotheses, and test some theories. This takes us through Bloom's fabulous stepwise process. We explore the knowledge, we gain some comprehension, we apply that knowledge to a situation, and then we enter, with the help of our teacher, into those upper levels of Bloom's taxonomical cognitive processes. Have a close think about your earth sciences. Have a close think about what it means to teach earth science. And if you're using it in assessment task 2, be sure, for instance, that you are talking in the language of earth science, that you are reflecting some of the systems and the subsystems, and you're embedding them in the correct spheres so that you're building student knowledge.